Welcome to the Deep Dive. We're here to explore the core ideas from texts that really shape our understanding. Today, we're jumping into Chapter 19 of Feynman's Lectures on Physics. This one's all about the center of mass and moment of inertia. So if you're wrestling with mechanics, maybe as a student, or you're just, curious, our goal here is to get past just memorizing equations. We want to give you that intuitive feel for why these ideas work, the logic Feynman was so good at showing.
Yeah, this chapter's pretty crucial. Up to this point, we often treat things like they're just points in space. But chapter 19, it finally tackles real extended objects, things with shape and size. And it shows how Newton's laws, like good old F-ma, still apply, even when things are spinning and tumbling.
Okay, let's unpack this then, starting with the center of mass, the CM. If you take some weirdly shaped thing like a wrench and you find that one spot where it balances perfectly on your finger, that's basically it, right? But what is that point, mathematically speaking?
Conceptually, it's this special point where we can imagine all the object's mass, the total mass m, is concentrated, just for looking at how outside forces affect it.
Mm-hmm.
And the power of this is huge. You can have something really complicated, a planet, a spinning top, even a cloud of dust, and just track the motion of this one point using S-ma. It simplifies things immensely.
And you said outside forces. That's the critical part.
Absolutely critical. Any forces inside the object, like the molecules pulling on each other, the stresses within the material, they all cancel out perfectly in pairs. They have zero net effect on how that center of mass accelerates through space. The object might be vibrating or flexing internally, but the CM sails along based only on external pushes and pulls.
So how do we actually find this point? Feynman gives a formula, or a jam. It looks like a sum of mass times position divided by total mass. It sounds kind of like an average.
It is exactly that. It's a weighted average of position. Imagine, like, chopping the object into millions of tiny equal bits of mass. The center of mass is just the average location of all those tiny bits. And it's weighted because if one part of the object is much heavier, it pulls the average position, the CM, closer to it.
Okay, that makes sense. And it leads to some neat shortcuts, right? Like for symmetrical objects.
For sure. If you have something perfectly symmetrical, think a uniform sphere or a rectangular block, or even a hoop, the center of mass is smack dab in the geometric center. The mass is balanced perfectly around that point.
And what about combining objects like two balls connected by a rod?
That's another great simplification. You don't need to reintegrate everything. If you know the center of mass for ball A, let's call its mass ML and position 6 hours, and for ball B, as a pointer, you can just treat them like point masses at those locations. The combined CM is then just the weighted average of those 2 points. The formula looks the same. The total mass times the total CM position equals 1 AC plus MB XB to OR. It's recursive, almost.
Now, here's something Feynman points out that I find, well, really profound. It's about scale. He says, this Feynman law for the center of mass works for something like a baseball, even though a baseball is made of zillions of atoms interacting via quantum mechanics, which is totally different from classical SME.
That is the deep point, isn't it? It's amazing. The laws of motion somehow manage to maintain their form across these huge changes in scale. You zoom out from the quantum fuzziness of atoms interacting, and suddenly the collective behavior, the bulk motion of the whole object, is described perfectly by this simple classical law acting on this one abstract point, the CM.
It's like nature's way of letting us approximate really complex things easily. We can figure out how a star moves without tracking every single atom inside it.
Exactly. So once we got this idea of the CM, the next practical step is finding it, especially for things that aren't simple shapes or symmetric. And that's where, yes, sometimes you do need calculus. Integration is basically just the fancy continuous version of that weighted average sum we talked about.
But Feynman gives some geometric examples, too, which are useful to visualize, like a simple flat right triangle.
Right. For a uniform right triangle, the CM isn't in the middle. It's actually 1/3 of the way up the median lines, measured from each corner. So it's closer to the heavier corner, the right angle corner.
And for a cone? A uniform cone?
For a right circular cone, it's even more shifted. The CM is 3/4 of the way up the central axis, measured from the pointy tip towards the base, or 1/4 of the way up from the base, always toward the bulkier end.
Okay, so we can find the CM. Now let's connect it back to forces, specifically gravity. Why does gravity feel like it pulls only on the CM? It's pulling on every atom, isn't it?
It is pulling on every atom. But think about rotation. If you assume the gravitational field is uniform across the object, which is a very good assumption for everyday objects near Earth, then the total turning force, the torque, caused by gravity around the center of mass adds up to exactly 0. For every bit of mass on one side, creating a torque, trying to turn it one way, there's a corresponding bit on the other side, creating an equal and opposite torque.
Ah, so they cancel out. That's why if you support something right at its CM, it balances perfectly. Gravity pulls down, but it doesn't make it turn.
Precisely. And this isn't just true for gravity, it's a deeper property of the CM. Imagine the object is inside an accelerating box, like a rocket taking off. Everything inside feels that inertial force pushing it backward relative to the box.
Yeah.
Well, that total inertial force also effectively acts through the center of mass, meaning the acceleration itself doesn't cause the object to start rotating relative to the box. The CM is truly the center for linear dynamics.
Okay, that solidifies the CM's role for linear motion. But what about rotation itself? If mass resists linear acceleration, what resists angular or rotational acceleration?
That brings us to the next big concept. The moment of inertia, usually labeled $, is basically rotational mass. But here's the key difference. Unlike mass, which is just a single number for an object, the moment of inertia depends entirely on which axis you're trying to rotate the object around.
How is it calculated?
It's defined as a sum. For every little piece of mass, $0 in the object, you find its perpendicular distance from the axis of rotation, square that distance, and multiply by the mass. Then you sum up all those mal Artatu 2 terms. Or to sum might raya 2.
That psi-squared term is really important, isn't it? It means mass that's farther away from the axis contributes much more to the rotational inertia.
Hugely more. That's exactly why extending your arms while spinning on a chair slows you down so dramatically. The mass hasn't changed, but you've increased its average square distance from the axis, so IL goes way up.
Feynman calculates it for a thin rod, right? Rotating at about its end versus its center.
Yeah, that's a classic example. For a uniform rod of mass $1 in length, if you rotate it about its center, the moment of inertia is ml 212 $2. But if you move the pivot point, the axis, to one end of the rod, the calculation gives a much larger inertia, R equals ml 202.33. It's harder to get it spinning about the end.
Doing that integral calculation every time you move the axis sounds tedious. There must be a better way.
There is, and it's incredibly useful. It's called the Parallel-Axis Theorem. This theorem is, well, it's a lifesaver for calculations. It says, the moment of inertia about any axis is equal to the moment of inertia about a parallel axis that goes through the center of mass, plus the total mass times the square of the distance between those two parallel axes. So the formula is just log ICM plus MR2.
Wow. So if you calculate dollars just once, which is often the easiest one to calculate due to symmetry, you can instantly find the inertia about any other parallel axis just using the total mass and the distance.
Exactly. And notice that since MR2 times is always positive, ICM is always the minimum possible moment of inertia for any set of parallel axes.
That's really elegant. And he also mentions another theorem for flat objects.
Right, the perpendicular axis theorem. This only works for flat planar objects like a sheet of metal or a disk. It says that the moment of inertia about an axis perpendicular to the plane, let's call it A zero, is simply the sum of the moments of inertia about any two perpendicular axes lying within the plane and intersecting the first axis, say, in the ups. So ECX plus IO, another handy shortcut.
Okay, theorems noted. Let's talk about energy and rotation. Kinetic energy. I assume there's an analogy here too.
A perfect analogy. Linear kinetic energy is 2 is 12 mv22. Rotational kinetic energy turns out to be 2 is 12 mv22. Here, our ideal is the moment of inertia we just discussed, and omega is the angular velocity, how fast it's spinning, in radians per second.
Let's use the classic example, the ice skater pulling her arms in.
Perfect. Skater starts spinning, arms out, large $. Then she pulls her arms in close to her body. This drastically reduces her $.
And because angular momentum, y omega, has to be conserved, assuming no external torque like friction, her angular speed omega has to shoot up, right? She spins much faster.
Exactly. Y goes down, omega goes way up to keep Lallard constant.
But wait, let's look at the kinetic energy formula again. Y omega 12 I omega 2 If 5L gets smaller, but omega gets much bigger, omega is squared.
Yes.
What happens to the energy?
Good question. If you work it out, because omega increases inversely with iodol, the kinetic energy actually increases. Tio goes up when she pulls her arms in.
Where does that extra energy come from? It seems like magic.
Not magic work. Remember, as she's spinning with arms out, her hands feel an outward pull that's the inertia resisting the circular motion, often felt as centrifugal force in the rotating frame. To pull her arms inward against that effective outward force, she has to exert a force over a distance. She has to do physical work. That work done by the skater is what provides the extra kinetic energy that makes her spin faster and hotter, so to speak.
Ah, okay. The energy comes from internal work done against the rotational motion. That makes sense. So this brings us to the perspective of someone in the rotating system, like us, standing on the rotating Earth.
Things get weird then, don't they? We need these fictitious forces.
Yes. If you insist on using Newton's laws directly within a frame that's rotating, which is a non-inertial frame, you find that objects don't obey Fifth unless you add some extra invented forces. Feynman calls them pseudo-forces.
And there are two main kinds he discusses.
That's right. The first one is probably more familiar, the centrifugal force. This is the force that seems to push things outwards, away from the axis of rotation. If you're on a spinning merry-go-round, you feel thrown outwards. In the rotating frame, you need this outward force to explain why things don't just fly towards the center, or why an object placed on the ride stays put relative to you. It's always directed radially outward. But it's fictitious, because someone standing still outside the merry-go-round just sees the object trying to go straight, inertia, while the merry-go-round turns underneath it. They don't see an outward force, they see an inward centripetal force needed to cause the circular motion.
Precisely. Centrifugal force is an artifact of being in the rotating frame.
Okay, what's the second one, the really tricky one?
That's the Coriolis force. This one is much more subtle. It only shows up when an object is moving relative to the rotating frame, and it acts sideways. It's always perpendicular to both the object's velocity relative to the rotating frame and the axis of rotation.
Can you give an example?
Imagine you're on a huge, slowly rotating turntable, like the Earth. Try to roll a ball straight outwards from the center. From your perspective on the turntable, the ball will seem to curve sideways. That sideways deflection is attributed to the Coriolis force in your rotating frame. Its magnitude is 2 millidortal omega VR dryer, where $5 is the radial velocity.
So if you're just standing still on the turntable, no Coriolis force.
Correct. Only when you move relative to the rotation.
Feynman derives an equation showing all the forces in the rotating frame, right? There's the real force, the centripetal acceleration term, the Coriolis term, and the centrifugal term.
Yes, he shows how the true acceleration, seen from outside, relates to the apparent acceleration, seen from inside, plus these extra terms. The Coriolis term, 2 meter away, is the one that depends on the velocity in the rotating frame and causes that sideways push. It's responsible for things like the swirling patterns of hurricanes.
It's a mathematical necessity to make Newton's laws appear to work when your viewpoint itself is accelerating.
That's a good way to put it. It patches up the laws for the non-inertial observer.
Okay, I think that covers the main ideas of Chapter 19. Let's do a quick wrap-up. We saw the center of mass as this amazing point that simplifies motion. All external forces act there for FMA. We learned how to find it using symmetry or integration.
Then we introduced moment of inertia, $1, as the resistance to rotation, heavily dependent on mass distribution and the chosen axis.
And the Parallel-Axis Theorem is the key tool for calculating IR easily once you know ICMO.
We touched on rotational kinetic energy, $12 I omega 22, and saw how internal work can change it, like in the skater example.
And finally, we looked at rotating frames and the fictitious centrifugal and Coriolis forces needed to explain motion from that accelerating perspective.
Absolutely. These concepts, CM and moment of inertia, they let us break down the motion of complex real-world objects into translation of the CM and rotation about the CM. They are fundamental tools.
And maybe a final thought to leave you with. Think about that scale invariance Feynman highlighted. That simple forlero applies to the center of mass of everything from a molecule to a galaxy. It makes you wonder, doesn't it? How much of the universe's complexity might just dissolve if we manage to find the right center, the right perspective to view it from?
A profound question indeed. Thank you everyone for joining us on this deep dive into Feynman's view on center of mass and rotation. We hope it clarified some things for you.